done first. Okay, I'm just going to start recording. Okay, yeah. Any preferences at all? Nope, no one cares. Okay, all good then. Then let's just go through all of them. Okay, so first one, let's look at these Feynman diagrams. So pretty much we're looking at all these different vertices, and we want to kind of make a judgment on whether they are allowed under the standard model, the normal standard model, without any weird extensions. And if they're not, then explain why they're not. So let's look at part A. So A is just electron coming in, electron going out, emits a photon. That's perfectly fine. That's just your QED vertex, the only one that's allowed. For the second one, you have neutrino going to a neutrino emitting a photon. So that's not allowed because neutrinos don't have electromagnetic charge. So nu E is not charged. So it can't have a coupling with the photons because photon carries the EM force. Okay, C looks like the first one, but yeah.
So what particle should be there instead of the proton?
Instead of a photon, you can put a Z boson there, so that's fine, because neutrinos are only coupled to the weak force. So the weak bosons can technically be coupled to them, but you're going to be careful because Z boson is neutral in charge. W has charge, so only the Z one can technically be connected this way.
Okay, so only the Z could be there.
Yeah, if it's just a neutrino in, neutrino out, no charge is being changed, then you have to.
That's why. So it can't be the W plus W minus.
No, because W plus W minus has to carry away some either a plus or minus charge. Yeah.
Yeah. Okay.
All right. Yeah. For C, a lot of reasons why you can't do this. First one is the fermion number is not conserved. You have an electron coming in, but then a positron coming out, and fermion number gets flipped when you go to the antiparticle. So if you have like a +1 particle here, you have a -1 particle here. So the fermion number is first violated. Charge is also violated. You have -1 electric charge, but now you have +1 electric charge. So that's also violated. And yeah, seeing these arrows pointing all towards the same vertex just looks funny. The ones that are allowed, the lepton, the fermion lines, the arrows come in and go out. So these, like the flow has to be conserved. So this one is definitely no. You can cite any of the reasons. D is fine. So that's the neutral current, what's it called? Neutral current coupling for neutrinos. Neutrinos come in, neutrinos go out, coupled to a Z boson that's electrically neutral. So everything's fine. Okay, for E, you have an electron going in, a muon going out, and then with a photon coupling. That's not allowed. So the thing we call here is the lepton number. So as you know, electrons, muons, and tau, they're pretty much like very similar to each other. They just kind of get heavier as you get to the later generations. They also carry like a distinctive quantum number called the lepton number. So you can't violate the lepton number in the interaction. So going in, you have +1 electron number, but coming out, you have +1 muon number. That's not allowed. And yeah, so this vertex is not in the standard model. Yeah, generally, if it's just an EM coupling, same generation, fine. Crossing generations, you have to go through some other fancy footsteps like footwork. This one's not going to work. Okay, and F, you have electron coming in, neutrino coming out, W boson. So that's okay, that's fine, because that's basically the weak decay, the beta decay, half of the beta decay. If you connect a up and down quark on the other side, then you have a full beta decay. So this is okay because electron carries a -1 charge. Doesn't say what W boson this is. So I can assume it's a W minus boson and it carries away the charge. So then outgoing the neutrino being neutral is perfectly okay. And electron and neutrino, they're both the first generation. So they both carry a lepton number. Oops. They both carry electron lepton number. So your lepton number conservation is also fine. Okay, this one, G, electron coming in, tau coming out, Z boson going through. No, same reason we cited here. You violate lepton number conservation. You can't turn an electron into a Z boson. Sorry, into a tau like this. Electron coming in, a muon neutrino coming out. That's not allowed. So that looks like this weak decay, but same generation only. You can't go from an electron to a muon neutrino. Has to be electron neutrino to conserve the lepton number. Okay, this one's definitely no, because this is a gluon. Electrons don't have color charges, so you can't have a coupling to the QCD boson. No color charge in electron. Okay, and this one, bottom quark, go into a gluon. I think that's fine. Did I say fine here? Yeah, that's fine. Yeah, that's just a standard color, the QCD interaction. Okay, similar thing, a down quark, but going to a strange quark and couple with a gluon. Not allowed. Down quark is not in the same generation as a strange quark, and plus strange quark carries an extra quantum number strangeness. And strangeness must be conserved under QCD. So this is a QCD interaction. QCD has to conserve strangeness. So you start off with 0 strangeness and end up with +1 strangeness. Or it's a -1. I think it's -1. Doesn't matter. You have a non-zero strangeness that violates it. Or a more straightforward explanation is that you're crossing generations again, and that's not allowed. Okay, this one, 3 photons coming together, definitely not allowed, because then we have confinement in the QED. Not a vertex in QED. If this is a vertex in QED, then you're running to the same problem in QCD where you can't separate quarks, and you wouldn't be able to separate electrons and protons anymore if this is the case. So definitely no. Okay, M, up quark, W boson. W boson has to carry away charge. This is just, it goes from up to up, so nothing's changed. So there's nowhere for you to find this charge for the W boson to carry away. So definitely no, violates charge conservation. Up to down quark with the W boson, that's okay. That's basically the other side of this weak decay. So the other side of beta decay. So yeah. And if you look at the up quark is what, plus 2/3 electric charge, and down is -1/3. So then the W plus boson can carry exactly 1 unit. So that's fine. Or maybe it's minus. But yeah, the difference of charge is 1 unit. So the W boson can carry 1, that's fine. Okay, this one, down quark to a top quark. Top quark is a 3rd generation. Down quark is a 1st generation. So no, can't do this. Last one, no, because not a vertex in QED. And yeah, this 4-point interaction will be like, it would technically be like this. Oops. So something in the middle like that. So if you had an electron, photon, and then a virtual electron as a propagator and an electron, photon. And remember last week we did the question where we said that if the mediator is extremely heavy, then this kind of approaches this 4-point interaction. But we know the mediator is not very heavy. The mediator is an electron. So it's definitely not like a heavy particle. So there's no reason for you to have this 4-point vertex, because you do have another one of these as well-defined in QED. And yeah, the bigger problem is that it's not renormalizable. So if you integrate over the momentum of these particles, then you end up getting an infinity. And that's not an infinity you can get rid of. Okay, any questions?
Could you go through all the rules and just list them out, if that's possible?
All of them? God, okay.
Well, because I remember you named about like 5 or 6.
Okay, yeah. The ones I can tell you the ones I listed. I don't think I can list all of them because I think it's
okay. Maybe not all of them, but the most common ones.
Okay, so you need lepton number conservation. You need charge conservation, of course. And you have what else did I say? Lepton number.
That was the generation one.
A generation one is pretty much the lepton number one. So like this one is, yeah, like generation.
What about strangeness number? Is that also?
That's just for, yeah, that's just for that one thing. So strangeness, it's a bit weird. So strangeness is conserved under QCD and QED. So for electric forces and color forces, it's conserved. But for the weak force, so under QFD, the flavor dynamics, then it is allowed to be violated. So if your particles involved are a strong force mediator or an electromagnetic mediator, then the strangeness has to be conserved. But if you have a weak mediator, then you technically can violate strangeness, but it's non-trivial. So I wouldn't pay too much attention to this. It's just unique to this one. I would just cite the lepton number conservation. So the generation conservation is probably more like applicable to like a general situation.
Okay.
Yeah. And what else? Okay, like ones like this, you just kind of have to know that there's only one vertex in QED. So if you see weird ones that doesn't look like that one vertex, you can like argue that it's not part of the QED theory. So yeah, this one's not really based on any conservation law or any kind of these rules. It's just saying that you don't see it in QED. The non-renormalizable conditions probably the most correct, but I don't think we want to go into that right now, so don't worry too much about it. Anything else? Lepton number. Yeah, it's pretty much all lepton number or fermion number. Yeah, and fermion number. So fermion number, you can also think of as particle versus antiparticle conservation. So if you come in with a certain number of particles, you have to come out with a certain number of particles. So you can't come in with one particle and come out with one antiparticle. That's not allowed. So that's another thing to look out for.
Okay, yeah, that looks good.
All right, no worries.
Thank you.
Okay. Let's have a look at this one. Dirac Lagrangian. So show that Lagrangian 1 is invariant under global symmetry, so not dependent on where you are, it's positionally. And the symmetry is a phase, so you go from your spinor to a spinor multiplied by a phase. Okay, so pretty much all you have to do is just to remember that the adjoint spinor basically transforms as just the complex conjugate of your normal spinor. So you get this. Okay, it's a phase, so it doesn't really matter, but normally you might want to just pay attention to the ordering. If it's like a matrix, and you have to be careful with the ordering. So normally you'll put the transformation on the right-hand side, just because the transpose thing, so you change the ordering. Like that. So, okay, then in this case, if we start with the Lagrangian and we transform it into, let's say, L dash, then that's equal to this thing, but then both of these spinors get to do their transformation. So we get psi dash I slash psi dash. And this is psi bar e to the I alpha I slash d minus m. Oops, forgot to put the e to that minus I alpha psi. Okay, so now alpha is just a number. Here is a global symmetry, so it's x independent. So alpha is just a number. If it's like a function of position, then this will be a local symmetry. So if it's global symmetry, that's good, because then this derivative wouldn't act on this exponential because there's no spatial dependence in it. So I can actually take this exponential to the left-hand side of this derivative without having any issues. So I can rearrange this by saying, okay, e to the I alpha, e to the minus I alpha, I d slash minus m psi. And then these two, as you see, cancel each other out. So then I end up with just L. So after this transformation, my Lagrangian did not change in form at all because I can move this exponential to the left-hand side. And that's all thanks to the global part of this symmetry. Okay, so that should be pretty good. Next one, show that the associated current is this. Okay, so this is gonna take a bit of writing. So let's just recall the surface term in the action variation. So if you remember in the lectures, you probably did something that's like you vary the action and then you demand that the action variation is equal to 0. And that basically gave you the Euler-Lagrange equations. So one of the terms gave you Euler-Lagrange equation, and the other one's a surface term that we said that because the surface can be taken arbitrarily large to infinity, and then as physics has to be finite, nothing should exist at infinity. So then that surface term disappears. So we're going to look specifically at that surface term. It's still going to disappear, but we're just going to use it to make an argument. So here, the surface term looks like this. So integrating over the boundary of the space that you're looking at, over the boundary, the sigma mu, and then you had this dl, the mu psi, delta psi in the in this delta s. So that was the second term. That's the other term. That's not the Euler-Lagrange term. So this thing equals 0 because we demand that it vanishes. But let's just look at this specifically. So let's say delta psi is the variation in the transformation. So in this case, our transformation was psi going to e to the minus I alpha psi. So if I take this as an infinitesimal, so like a Taylor expand this Taylor expand this to get like the infinitesimal transformation, then I'm going to get 1 minus I alpha psi. So then this is equal to psi minus I alpha psi. So this part is the small change. So this is the delta psi. So this is like modifying my original psi a little bit. So that's what the transformation is doing. So psi prime is equal to psi plus this a little bit. So this is equal to minus I alpha psi. And I put this in here, so I get integral over the boundary d sigma mu minus I d L d mu psi, and then psi. Oh, and then there's an alpha somewhere. Yeah, and an alpha here. Oh yeah, cool. So now I'm gonna rewrite this as dr, the integration, but then I'm going to call this thing a j mu nu, and then times by something called delta omega nu. So here, all I did is I'm saying that I have this tensor term, j mu nu, which I've now defined to be everything here that's not alpha, minus I dl d mu psi. And then this delta omega nu is equal to alpha. It looks a bit weird, but the reason I do it this way is because in this case, we're only talking about variations in the field. So we're only modifying the field with some like gauge transformation. But in general, this argument works even when you're doing some space-time Lorentz transformation. So that's why you write it in this way to have this d omega nu term to kind of give you the contingency that you can actually make this small parameter a space-time dependent quantity. But in this case, our small parameter is just alpha, which is in this gauge transformation. And since it's global, it doesn't depend on anything. So it's just a number. But like this is leaving us the possibility that we can make this a full 4-dimensional space-time infinitesimal. Okay, so now with this, this is a surface term, and this has to vanish. And I'm just going to first rewrite this as dr d4x d mu j mu nu delta omega nu. So going from this step to this step is just using divergence theorem. So I take it a surface integral, and I say, okay, whatever's on the surface has to be what is actually like leaving the volume. So it can transform the surface integral to a volume integral with the divergence theorem. And I pick up this divergence term in 4 dimensions, so d mu j mu nu. Okay, cool. So now this whole thing has to equal to 0. And obviously, the only thing that could be equal to 0 is the d mu j mu nu term, because we know this d omega term is an arbitrary infinitesimal that we choose to be non-zero. So this can't be 0. So this has to be equal to 0. And that's the conserved current. Whoop. I'm getting a phone call. I'm just going to get rid of that. That's conserved current. So yeah, this is basically, this argument is what we call deriving the Noether current. So it's using Noether's, it's basically Noether's theorem to show that you can basically derive a conserved current this way. And okay, now that we've gone through all of this, let me just move this down a bit. The whole point of going through all this is just to convince you that this expression for the current is like in general correct. So we're going to use this to actually work out what the current is. And okay, J mu nu equals minus I, and then dl d psi. So that's just taken from the Lagrangian here. So if I just take a derivative with respect to this psi, I'll just be left with this coefficient in front here. So I have where did we go? Minus I psi I gamma mu psi. And that is equal to psi bar. Sorry, this is psi bar here. So equal to psi bar gamma mu psi, because the i's cancel out and that's it. Yeah, so that's how we get the current. Any questions? Okay, cool. So if not, then let's look at the conserved charge. So we have the current now. So then let's define the charge. Q nu is equal to, not nu, sorry, this is a V. So QV, basically saying the amount of charge in some amount of volume is me integrating over this volume, d3x. It's a spatial integral, so we only care about like spatially how much charge is in this volume, so it's not d4x. And then I'm going to call this J0 nu. So this is kind of like a statement. We have to check that this actually is a charge and is actually conserved. So usually to do that is dqv dt, check that it's actually constant in time, so it's conserved. Then we get d3x d0 J0 nu. So d0 is just ddt, so going in here. But now before here, we show that the current is conserved. So d mu j mu nu equals 0. If I write this out in terms of components, I get d0 j0 nu minus di ji nu is equal to 0. So then I can write this as d3x di ji nu, because this is because of this relation. Okay, and now I'm going to use the divergence theorem again, but I go backwards. So I go from a volume integral to a surface integral. So here we have a divergence here. So if I go back to a surface integral, so going back to the boundary of dv, integrating over the boundary, then I just have the current. And okay, dv can be taken to infinity. So this boundary, this volume could be arbitrarily large. I can take this boundary to infinity, and from there I can say, okay, at infinity, your current should vanish. Should be 0 at infinity. So therefore, this term goes to 0. And therefore, you can see that the charge is conserved. And this will be the correct expression to use for defining the charge. And once you set that, then it's pretty easy. Just take this in, and you just get d3x psi bar gamma naught psi. So the mu is just 0. Then that equals d3x psi dagger gamma naught psi. The gamma naughts cancel out, so you end up with just d3x psi bar, not psi bar, sorry, psi dagger psi. And that's what we wanted. These should be things that once you derive once, you can just quote them. You shouldn't like need to derive this every time you want to use it. Okay, all good. All right. If no problems, then let's move on to the next part. Here we go. Okay, isospin. So in this problem, we're looking more detail at the SU2 symmetry. So it's okay. We've been through this last week, or a week ago. So it's just 2x2 symmetries, and we can show that you can express them in terms of these Pauli matrices. So as an exponential of I times these like contraction of the sum, so sum of the three linear combination of the three Pauli matrices, they can generate any SU2 symmetry matrix. So for the first part, we want to show that this H tilde times I sigma 2 H star transforms under SU2 symmetry, as we expect. Okay, so the question kind of didn't make it more specific. It should say that we know that H transforms under SU2 symmetry like this. And we're going to use this fact to try to argue that H tilde also transforms under SU2 symmetry the same way. Okay, so to do that, let's just get into it. So H tilde going into U times H tilde. So writing it into here, I'm just going to get, okay, before the start, I should say that U is going to be taken as 1 plus I alpha j sigma j. So it says consider the infinitesimal transformation. So I'm just going to take the Taylor expansion form of U for this. So okay, then this equals I sigma 2. These don't get transformed, so they're fine. So I'm just going to get 1 plus I alpha j sigma j H, and the whole thing starred. So I'm transforming the H star here. That's the only thing that transforms under SU2. Okay, and then now I just have to multiply them in I sigma 2, and I get a H star from the 1 here, and then minus I, because I have to conjugate everything in this bracket, minus I alpha j, and then sigma j, this gets conjugated. Sigma 1 and 3 are real, so they don't care, but sigma 2 is complex, so you do have to remind yourself to complex conjugate this thing. And then H star. Okay, so now I'm gonna go back and look at the initial relationship here. So initially I had said that H tilde is equal to I sigma 2 H star. If I multiply both sides by I sigma 2 squared H star. I'll prove this explicitly later, but this is equal to -1. So this is equal to minus H star. So I can say that H star can be brought back, like an inverse will be H star equals minus I sigma 2 H tilde. So I'm going to use this identity for now, but I will show you. I'll show you later. It'll become obvious later why this is the case. So okay, I'm going to plug this back into here, into the H star. So I end up with I sigma 2 H star plus I alpha j sigma j star I sigma 2 H tilde. I don't know why I wrote this upper index, but you get it. It's not squared. It's the upper index sigma 2, but it doesn't really matter. Okay, now I'm just gonna expand the thing out. So H star times I sigma 2. So this is just H tilde. So the first term is just back to H tilde, and then plus. Oh, sorry, not plus. So plus I'm gonna multiply two of these together. So I get a. I'm just gonna keep the I for now. Plus I sigma 2 I alpha j sigma j star I sigma 2 H tilde. Okay, cool. Now I'm just going to collect all the imaginary units. I tilde minus I alpha j, and I'm going to group all the sigma matrices together. Careful with the ordering because they're matrices, so you can't flip the order. So sigma 2 sigma j star sigma 2 H tilde. Okay, so at this point, you're gonna have to do something real weird to simplify this any further. So let's look at, firstly, the commutator for sigma I, sigma j. So commutator for this is I2 epsilon ijk, sigma k. And also take the anti-commutator. The anti-commutator of the Pauli matrices is just 2 delta ij I. Okay, so having these two, let's first work with the anti-commutator. So I guess sigma I, sigma j plus sigma j, sigma I is 2 delta ij I. Yep. And then now I rearrange to say sigma j, sigma I is equal to 2 delta ij I minus sigma I, sigma j. Okay, and using this identity, I'm going to plug this into the left-hand side of the commutator. So the commutator will be sigma I, sigma j minus sigma I. Sorry, sigma j, sigma I. Okay, so I'm going to plug this into the second term here. So I'm going to get minus 2 delta ij I plus sigma I, sigma j. And this whole thing equals 2i epsilon ijk sigma k. Okay, so collect these two together, you get factor 2, all the 2's cancel out. So finally, I get this relation saying sigma I, sigma j is equal to I epsilon ijk sigma k plus delta ij I. This is the identity matrix. Cool. Okay, so this is the core equation I'm going to use. And this actually explains how I managed to get this relation here. So you can see that take the I squared out, you get a -1. And then sigma 2 squared. Sigma 2 squared just be sigma 2, sigma 2. And ij are the same. So this Levi-Civita symbol drops out. And you end up with just this Kronecker delta. And that's just equal to 1. So that's how I got from this step to this step. Is just using this relation. And yeah, I'm going to use this relation to simplify this expression here. And the way to do it is to look at, so we have sigma 2, sigma j star, sigma 2. So let's look at each one of them individually. So sigma 2, sigma 1 star, sigma 2. Sigma 1 is a purely real matrix. So starring it doesn't do anything. So it's just equal to sigma 2, sigma 1, sigma 2. So first, let's look at the second one. So sigma 1, sigma 2. From this, we see that the Kronecker delta drops out because I and j are different. The Levi-Civita will be I equals 1, j equals 2. So k must equal to 3. So 1, 2, 3, that's a like, what's the correct word for it? Like a clockwise permutation. So this is +1. So this equals sigma 2, I, sigma 3. Okay, and then now sigma 2, sigma 3, putting into here, I equals 2, j equals 3. I equals 2, j equals 3, k equals 1. 2, 3, 1 is still a clockwise permutation. So this is still +1. So I get equal to I times I sigma 1. So that's equal to minus sigma 1. So this whole thing, you can actually cancel everything out to become just minus sigma 1. And doing the exact same thing, let me move this window. Okay, doing the exact same thing. Now let's look at sigma 2 star, sigma 2. And okay, sigma 2 is a complex matrix. So when you star it, you get the minus sigma 2. So this is equal to minus sigma 2, sigma 2, sigma 2. Okay, sigma 2 just equals +1 as we're shown here. So this just equals minus sigma 2. That's the easiest one. Final one, sigma 2, sigma 3 star, sigma 2. Okay, sigma 3 is also real. So this is sigma 2, sigma 3, sigma 2. Okay, but when you look at the second term, sigma 3 and sigma 2, I equals 3, j equals 2. So you got 3, 2, k equals 1. So 3, 2, 1, that's an anti-clockwise permutation. So Levi-Civita equals -1 in this case. So I get minus I sigma 2 sigma 1. And then I do this 2 1 in here again. The Levi-Strauss again is anti clockwise. So I get plus I sigma 3. And the 2 i's equal minus 1, so minus sigma 3. Ooh, okay. So that was a lot of talking, but the whole point here is to see that when you do all this, you end up with just the middle one, whatever j equals, you get a minus sign times sigma of that particular Pauli matrix. So this just equals minus sigma j. So if you sandwich a sigma matrix with 2 sigma 2s, then you're just going to end up picking up a minus sign from the middle. Everyone happy with that? Is that all good? No questions? Okay, then in that case, I could just put this minus sigma j back into here. So this equals h tilde plus I alpha j sigma j h tilde. And voila, 1 plus I alpha j sigma j. So this thing is the U matrix, so it's h tilde U. So, okay, I wrote it the wrong way around, but it doesn't matter. The ordering, the thing technically goes to the left, but okay, I should be precise about that. Erase that. So the h to the right hand side of the sigma matrix. So technically, when I factor this out, I should get 1 plus I alpha j sigma j h tilde. So then the U is on the left hand side, and that's important. Okay, cool. So our h tilde transformed into U tilde as expected. So therefore, say it does transform under SU2 as expected. So yeah, it's a bit weird. The wording should be a bit more elaborate. So it should say that because H transforms under SU2, we then have to show that H tilde also transforms under SU2. Because here what we showed is basically H tilde transforms when we transform H, and then everything comes out to show that H tilde also comes up with this factor of U in front. So it's leveraging the fact that H transforms under SU2 that we make this conclusion that H tilde also transforms under SU2. So it's not the most precise wording, but it gets the point across. Okay. All good? Any questions? Okay, so then no questions. And next one, consider 2 scalar fields phi I. Transforms under SU2 as this. So it's just a real scalar doublet. And then you want to write down the Lagrangian for the 2 scalar field, which is quadratic in the field and invariant under SU2 transformation. So this is pretty trivial. So the Lagrangian will just be the kinetic term, d mu phi. But to make sure they transform under SU2, you have to dagger one of them. So this one will come with a factor of U. This one will come with a factor of U dagger. And when they come together, U dagger cancels out, so it's fine. And then you also have a mass term, m squared, m dagger, phi dagger, sorry, phi dagger, phi. And so when these two transform, one comes with U, one comes with U dagger, they cancel each other out, we're all fine. And that's the best you can do. You can't, only quadratics, I can't have any higher powers of phi, and there's no other terms you can write down. You might be tempted to write down something like d mu phi dagger phi. That doesn't really make any sense, because if you think about this as a physical interaction, you basically, this is the propagator, so it's just saying my phi particle propagates along. This thing is saying that it propagates and then suddenly somehow gets tripped over its own momentum and then just turns back into a non-propagating phi, and it just stops there. So it doesn't make any physical sense, so you can't include this term in there. And the next logical term is phi to the 4, but we're stopping at quadratic order, so that's really all we're doing. So derivative coupling is okay for 3 particles, for 3 fields, not for 2 fields. So if you have another phi in there, then this could make sense. Okay, this one's just that. It's just writing down Lagrangian. There's nothing else to it. You can't go through and show that it transforms on the SU2 invariantly, but it's not much to actually show. Okay, promote the global SU2 transformation to a local one. So now my U equals e to the I alpha has a X dependence in here. So that means I can't easily pass these things through derivatives. It's gonna get differentiated as well. So you're gonna have with a bunch of chain rules. So now I have to modify the Lagrangians. I'm modifying this Lagrangian, so then it's actually invariant under the local SU2 as well. So the way to do this is just write your L, replace your derivative with covariant derivative. D mu phi. Don't have to do anything to the mass term because this one doesn't have any derivatives. So even if the transformation is local, they still cancel each other out because there's nothing stopping them from sticking together. And the tricky part is this covariant derivative now has to take the form plus IG A mu comes with the gauge field. So it's pretty much just a higher dimensional version of the QED version that you saw. So A mu is transforms to A mu prime equals to U A mu U dagger plus 1 over IG U dagger D mu U. Okay, and I'm not going to try to show you if it works because there's a lot of lines. I don't think you'll be expected to explicitly show this because that's a lot of writing. But yeah, so if you take the limit that U is equal to just the phase e to the I phi, then you recover the electromagnetic version. So you get back the QED gauge fields. It's just that here now you have a more non-trivial representation of the unitary transformation. Any questions?
Could you just explain what this actually has to do with isospin?
Oh, isospin is so basically it's a historical thing. So when they first figured out that protons and neutrons are pretty much the same mass and they look almost like each other, the difference is just that the charge. So they thought there's like a twofold symmetry between protons and neutrons. So someone first proposed this SU2 symmetry to use on proton and neutrons. And then later they realized that the symmetry is not within the protons and neutrons, but is with the quarks underneath. So it kind of got stuck as like a historical term. But when they say isospin symmetry, it usually just refers to a twofold symmetry that's governed by SU2. So it's more or less a SU2 study rather than anything particular with the nuclear isospin.
Right. Okay. Thanks.
All right, nice. Okay. Yeah, if no problem, then okay, let's try to do this. And we'll get another 5 minutes. Okay, so this one you have a very large gauge group. So this is the full standard model group. So you got all 3 symmetry groups, like you can think of them as multiplied together, but it's like composed together. And then now you want to consider the Higgs boson H, and then these spinors. So the left-handed quark, capital Q means quark, and then you have the up and down quarks that are right-handed, and then capital L is leptons. So you got the left-handed leptons and the right-handed electron. So now you want to consider that each of these individual spinors, these fields transform under these 3 groups represented by this. So the way to read this is that the first one tells you which SU3 representation that you are transforming under. So 3 means that you're transforming under the 3 representation. So that's like the triplet. So having the 3 colors in the SU3 that you flip them around. And this tells you that quarks, they have colors, so they will transform as a triplet under SU3. Whereas something like an electron, which doesn't have a color charge, so it doesn't care about color QCD, quantum chromodynamics. So this one has a singlet. So that means singlet means you don't get transformed under SU3 at all. And that makes sense because electrons don't care about what QCD is doing. And then the second number is the SU2 representation. So this one tells you that, okay, leptons, they have an SU2 two representation. So that's the isospin, not isospin, like the twofold symmetry that we talked about before. So you can flip up and down quarks, like top and bottom quarks and stuff like that. So these leptons get flipped, but the Higgs boson also has a 2 here, but the quarks don't. So I'm sorry, then I shouldn't say up and down quarks get flipped. It should be the flavor changes, the generational changes that it gets this. So not the up and down stuff. And then the third one is just the U1 charge. So in this case, it's just the electric charge. So electrons have -1. These guys have the quarks have their charges, and the Higgs have a charge as well. So this just tells you all the information about how this particular spinor transforms under this field. Okay, and now what we want to do is list the combination of up to 3 fields. So linear combination of 3 of these that are invariant under both Lorentz and the G transformation. The G's are invariant under all 3 of these transformations. Okay, so from the lectures, I hope you remember that psi bar psi is the only scalar under Lorentz transformation, under Lorentz group. So that tells me that we have to pair these things up in pairs first to make them Lorentz invariant. And okay, to make it distinguished, I'm just gonna say psi bar chi. Chi is just another way of saying a spinor, but it's just to tell you that they don't have to be the same thing, could be different. Now, with this, then you have to then notice that only the left and the right-handed couplings can work. So I can't have something like psi bar left, chi left, because then this thing equals psi dagger gamma naught left, chi left, and this equals PL projection dagger gamma naught PL chi. And then once I take this apart, I get psi bar PL gamma naught PL chi. And okay, and then I can write this as psi bar again, and I get an extra gamma naught at the front, at the left. PL chi. And then remember that PL gamma naught is equal to gamma naught PR. Then I can do it to one of these. So I end up getting psi bar gamma naught PR PL chi. Now, projecting left and right-handed components at the same time means that this has to be equal to 0. So same argument could be made about why psi right, chi right can't work as well, because both of these, you end up projecting both components consecutively, and that will just delete the whole thing. Okay, so if I can only have these two, then using the fields I have, that means the only allowed ones are QL, UR, QL, DR, QL, ER, L bar L, UR, L bar L, DR, and L bar L, ER. And then plus all of the Hermitian conjugates. So you can have E bar R, E bar L, L, R, but oh, sorry, you just move the bar across if you want, but no point writing them down. Okay, so for the 6 of these, under first SU3, let's look at SU3. It has to, these have to be transformed under SU3 invariantly. So that means when you add them together, when you add the SU3 charges together, they should have no SU3 charge. They shouldn't transform at all. So in this case, you can see that, not U, sorry, QL bar UR. So this transforms under 3 inverse transform. This one transforms as 3, so 2 of them cancel out. Whereas this one this transforms as a singlet in SU3, but this one transforms as a 3. So then these two added together, it will not be invariant under SU3. So this one's not allowed. So this one, SU3, inverse SU3, good. Inverse 3, forward 3, good. Inverse 3, singlet, no good. This one, they're both singlets, so then that's actually good. Singlet, forward 3, so no good. So we end up only with 3 that fits this description. So QL, DR, and then L bar L, ER. These are the 3 that only these 3 are invariant under SU3 symmetry. And then when we look at SU2, then all 3 above, if you look at how the SU2 symmetries add together. So Q has 2, U has 1. So them added together will just have a 2. And then L has a 2, E has a 1. So those 2 added together would just be a 2. So all of these, all 3, have inverse 2 rep under SU2. So they're all transformed inversely under SU2 symmetry. So to make them transform as a singlet, we have to add a forward SU2 symmetry, forward 2 rep transformation. And luckily, the Higgs boson transforms as a forward 2. So if I simply add the Higgs to them, then they are now SU2 singlets. What bar here? L bar L, E R H. And as we saw before, H tilde also transforms under SU2. So this also transforms under SU2. So H tilde can work as well. QL, UR, H tilde, QL, DR, H tilde, L bar L, ER, H tilde. So we kind of go back to 6 combinations again. So the final deciding factor is a U1 charge. So if I want to be invariant under U1, then all the electric charges has to cancel out, or like the U1 charge, okay, electric charges must cancel. Now, okay, if you look at some of them do cancel, some of them don't. The H tilde, one thing to notice is that it looked like this. And this is the charge conjugation operator. So H tilde has a U1 charge of minus a half. Sorry, plus a half. Because the Higgs boson has charge minus a half. So H tilde is just the Higgs boson, but charge conjugated. So you get a plus 1/2 charge. So then let's look at QLURH. QL bar has minus 1/6, so minus 1/6 for this. And then U has plus 2/3, so plus 2/3. And then H has minus a half, minus a half. And that, if my math is not completely dumb, this is equal to 0. So yeah, this is good. So that means QLURH is a singlet under U1. Is singlet. And then if you go through all of these and you realize that some of them don't add up, like this one doesn't, this one ends up with minus 1 charge. So if it's minus 1 charge, it's not going to transform invariantly under U1. So after looking through all of this, you find that QL bar DR, QL bar URH, QL bar DR H tilde, and then L bar L, ER H tilde. These 3 are singlets under all of the SU3, SU2, and U1 symmetry, and they are Lorentz invariant. So these 3 actually form the Yukawa sector. And that's how your quarks and leptons get mass via the Higgs mechanism. I think I went through it a bit quickly, so I'm going to ask Mikhail to maybe go through it again a bit more carefully. But the idea is pretty much just looking through these charges, and then in the SU2, SU3 part, you have to be a bit careful to convince yourself that they actually have a forward and inverse transform under the representation and they cancel out. And then for the U1 part, just make sure the charges actually numerically cancel out. Yeah, so if you want to build models, then you have to go through this exercise with all of the fields that you have to try to figure out which ones are actually going to be invariant under your Lagrangian. Any questions? Yeah, this is pretty cool. Yeah, it's a bit out there though. I'm surprised Mikhail put this in this. I feel like this is like, I don't even think they taught this in QFT in 4th year. No questions? If not, then thanks for your attention, and I'll see you guys next week. Let me stop.